In October 2012, a research ship was crossing one of the least familiar stretches of the Pacific Ocean when the scientists aboard noticed something strange on their maps. According to one set of data, there was an island ahead. Not a rock. Not a tiny reef. An island roughly 25 kilometers long. Big enough that if it existed, nobody standing on the deck should have had much trouble seeing it. It had a name. Sandy Island. It appeared in scientific databases. It appeared in global maps of the Earth's coastline. It even appeared in Google Earth. But there was another map aboard the ship. The official navigation chart. And on that chart, Sandy Island wasn't there. The scientists had two versions of the planet in front of them. One said there was land. The other said there was ocean. And because they happened to be on a ship in exactly the right part of the world, they could do something most people arguing over maps cannot. They could look outside. There was no island. Just ocean. So the crew began measuring the water beneath them. If Sandy Island had recently disappeared beneath the waves, perhaps they would find a shallow reef. Maybe the summit of an underwater volcano. Maybe a sandbank lying just below the surface. Instead, their instruments told them something much stranger. The seafloor was more than a kilometer below the ship. In places around the supposed island, earlier hydrographic measurements were even deeper. This wasn't an island that had recently sunk. There wasn't enough mountain beneath it to have been an island in the first place. And that created a remarkably simple question. How does an island that apparently never existed end up on maps for more than a century? Because Google had not invented Sandy Island. Google had inherited it. Scientists had inherited it. Global databases had inherited it. And once researchers began tracing the island backward through history, they found something more interesting than a simple Google Maps mistake. They found an error that had learned how to survive. It moved from sailors to paper charts. From paper charts into digital databases. From one database into another, and eventually onto screens used by millions of people. At one point, some scientific datasets even contained measurements that seemed to confirm the island was real. Except those measurements weren't independent confirmation. They were echoes of the same original mistake. Sandy Island had become something extraordinary. A piece of geography created not by geology, but by information. And when scientists finally removed it from the map in 2012, one part of the mystery remained. Someone had reported seeing something in that part of the ocean back in the 19th century. So what did they actually see? To understand that, we need to travel to the Coral Sea. Between the eastern coast of Australia and the islands of New Caledonia lies a huge expanse of Pacific water. There are real islands here. Real reefs. Underwater ridges. Volcanic structures. Shallow banks. And enormous areas where the bottom falls far below the surface. It is exactly the kind of region where maps matter. For an airline passenger flying overhead, a mistake of several kilometers might mean very little. For a 19th century ship captain, an island drawn in the wrong place could matter enormously. Sailing ships depended on charts not merely to know where they were going, but to know what could destroy them along the way. A reef that rises from deep water might be nearly invisible until a vessel is already dangerously close. An island incorrectly omitted from a chart could become a wreck. That created an understandable bias in early hydrography. When sailors reported a possible hazard, mapmakers had reasons to take the report seriously. Better to warn future captains about an island that might exist than pretend dangerous land definitely wasn't there. And the world's oceans were still being mapped through an accumulation of voyages. One ship sees a reef. Another ship fails to see it. A captain estimates a position. A hydrographer compares reports. A cartographer decides what belongs on the next chart. Modern maps can make geography feel permanent. Coastlines appear as clean lines. Coordinates contain precise numbers. Zoom in and roads appear. Zoom farther and buildings appear. It gives the impression that the map is simply a photograph of reality converted into symbols. Historically, maps were something very different. They were arguments. Every line represented somebody's belief about where something was. Sometimes that belief came from direct measurement. Sometimes from older maps. Sometimes from a report. Sometimes from a sailor who had passed through once. And sometimes the report was wrong. The ocean became filled with what later cartographers called phantom islands. Places that appeared on maps, sometimes for generations, before explorers discovered they weren't there. Some originated in navigation mistakes. Some from misidentified clouds. Some from floating ice. Some from reefs whose locations had been recorded incorrectly. Some may have represented real features placed at the wrong longitude. And once an island entered the cartographic record, deleting it could be surprisingly difficult. Because absence is harder to prove than presence. A captain who sees an island can write, "Island here." A captain who sees nothing cannot necessarily write, "No island exists." Maybe he passed 10 kilometers too far east. Maybe haze concealed it. Maybe his own position was wrong. Maybe the earlier captain was right and he was wrong. So uncertain features could survive. Sandy Island appears to have entered this world in the 19th century. The scientists who investigated its history after 2012 found that the first chart clearly corresponding to the modern phantom Sandy Island was a British Admiralty chart published in 1908. But the chart did not claim that British surveyors had personally discovered the island that year. It traced the report much farther back, to 1876, and to a vessel named Velocity. Velocity was a whaling ship. According to the chart, its crew had reported an island in roughly this part of the Coral Sea. That observation became the ancestor of Sandy Island. But something about the geography was already strange. Other features named Sandy Island had appeared on older maps. One had been associated with the voyages of Captain James Cook. But those islands were in different locations. The Sandy Island that eventually became famous in 2012 occupied a position around 19 degrees south and 160 degrees east. Roughly 500 kilometers northwest of New Caledonia. An isolated patch of supposed land. Over time, charts reproduced it. Its dimensions became more concrete. Its shape became an elongated strip. And an uncertain 19th century observation began looking like ordinary geography. That transition is important. The first person to report something may be uncertain. The second mapmaker copies it. The third sees it on 2 maps. The fourth sees it on 3. Soon the number of sources appears to grow. But the number of independent observations may still be 1. This is one of the oldest problems in information. Repetition looks like confirmation. Imagine hearing a strange fact from one person. Then reading the same fact in 3 books. Then seeing it in an encyclopedia. Eventually the fact feels well established. But what if all 3 books copied the same first person? You do not have 4 sources. You have one source repeated 4 times. Sandy Island would eventually demonstrate that problem at planetary scale. But before the digital era, hydrographers actually began becoming suspicious. Ships continued traveling through the Coral Sea. And people kept failing to find Sandy Island. That mattered. One missed sighting proves little. Repeated failures begin changing confidence. Hydrographic charts developed a way to communicate that uncertainty. Beside Sandy Island appeared 2 small letters. ED. Existence doubtful. Those 2 letters tell us something fascinating. Long before Google Earth displayed Sandy Island, professional navigators already knew something was wrong. The island had not simply been accepted without question for 136 years. There were effectively 2 cartographic traditions developing. One treated the feature cautiously. Another allowed it to survive as land. Eventually, hydrographic surveys went farther. Modern echo sounding allowed ships to measure the depth beneath them. Instead of simply looking for an island above the horizon, surveyors could examine the shape of the seabed itself. That creates a powerful test. Suppose an island had existed recently but had eroded away. You would still expect a geological structure beneath it. An underwater mountain. A reef platform. A volcanic summit. Something reaching relatively close to the surface. An island cannot simply vanish and leave 1,400 meters of empty water beneath where it stood. Geology doesn't erase mountains like a drawing from paper. Australian hydrographic measurements around Sandy Island found depths between roughly 1,500 and more than 2,000 meters. There was no hidden island. No shallow summit. No reef waiting a few meters below the waves. The French Hydrographic Service had enough. In 1974, Sandy Island was removed from official French hydrographic charts. The Australian Hydrographic Service eventually did the same. By 1985, as far as the professional hydrographic authorities responsible for safe navigation were concerned, the phantom had essentially been dealt with. Sandy Island did not exist. The information was communicated internationally. And if this story had happened a century earlier, that might have been the end. A questionable island appears. Better surveys arrive. The island is crossed out. Maps improve. Except this was happening just as mapping itself was undergoing one of the largest transformations in its history. The world was becoming digital. Paper maps have an obvious limitation. Every map is a physical object. If something changes, someone has to publish a new version. A corrected chart must replace an old chart. That can be inconvenient. But paper also has one accidental advantage. Errors are often trapped inside individual documents. A mistake on one chart does not automatically rewrite every other map in existence. Digital data works differently. A digital coastline can be copied, merged, reformatted, embedded inside software, used as the foundation for another database. That new database can become the foundation for another. And suddenly one mistake isn't living on one chart. It is reproducing. During the transition from paper charts to digital geographic information, a major global shoreline database was created. It became known as the World Vector Shoreline Database. Its purpose was enormously useful. Instead of every scientist or mapping program having to redraw the coastlines of the entire planet, researchers could use one standardized digital representation. Think about what that means. Every continent, every major island, thousands upon thousands of kilometers of coastline, converted into coordinates, lines, polygons, a mathematical description of where land ends and ocean begins. Once that information exists digitally, an extraordinary number of things become possible. Scientists can model ocean circulation. Climate researchers can separate land temperatures from sea temperatures. Mapping programs can draw continents at different scales. Geologists can overlay tectonic information. Software can calculate distances. Satellite images can be processed automatically. But there is a hidden assumption inside all of those operations. The coastline database has to be right. And the World Vector Shoreline inherited Sandy Island. Somewhere during the process of converting historical geographic information into digital form, the phantom made the transition. It had survived paper. Now it became data. And data is where Sandy Island gained something close to immortality. Because digital systems trust other digital systems. Suppose you are building a global data set of ocean temperature. A satellite measures temperatures over the Earth's surface. But your software needs to know which measurements represent ocean and which represent land. You don't want sea surface temperature algorithms trying to process the middle of Australia. So you use something called a land mask. The concept is straightforward. Give the computer a map. Everything inside these boundaries is land. Everything outside is water. The program then treats pixels differently depending on which side of the boundary they occupy. But what happens if your coastline database contains an island that doesn't exist? The land mask contains it too. Your satellite may be looking directly at open ocean. But the software has already been told. that area is land. So it may discard the ocean measurement, or leave a blank, or substitute an elevation. Now another researcher downloads your processed dataset. They see a blank patch surrounded by ocean. Why is the satellite not measuring sea temperature there? Because it's land. At least according to the data. A false island has now generated what looks like independent evidence of itself. This is where the Sandy Island story becomes almost absurd. After the 2012 expedition announced that the island wasn't there, some scientists were initially skeptical. Not because they distrusted the people on the ship, because other global datasets appeared to contain the island too. Bathymetric databases showed it. Some terrain models assigned it an elevation above sea level. Certain satellite-derived products treated the area like land. One model effectively said the island rose about a meter above the sea. Another placed it around 2 meters. The evidence seemed to multiply. A coastline database said island. A topography database said island. A satellite product behaved as though there was land. Google Earth showed an island-shaped gap. Could all of those systems really be wrong? Yes. Because they weren't truly independent. They were related. They had inherited the same assumption. The island had entered the world vector shoreline. Other databases used that shoreline as a land mask. Products derived from those databases repeated the geometry. Then people looked at several products and naturally assumed they represented several observations. But underneath them was the same ancestor. One old cartographic mistake. This is one of the most important ideas in the entire story. Data can agree with itself. That does not mean reality agrees. If 10 computer programs all draw information from the same incorrect source, you can have 10 matching answers and still be wrong. The problem becomes even harder when the systems are complicated enough that nobody remembers exactly where every input originated. A scientist downloads a global bathymetry grid. The documentation says it combines satellite measurements, ship surveys, and coastline information. The researcher has no reason to inspect the 19th century history of every island. Why would they? There are thousands. The database exists precisely so they don't have to reinvent the map of the planet every time they perform an experiment. This is the value of shared scientific data. And Sandy Island revealed its vulnerability. A useful dataset becomes widely adopted because people trust it. The more widely it is adopted, the more systems inherit its assumptions. The more systems inherit those assumptions, the more established the underlying information appears. An error gains authority through popularity. By 2012, Sandy Island was no longer merely a mark on an old nautical chart. It existed in an ecosystem of information. Then the ROV Southern Surveyor arrived. The scientists aboard were not searching for phantom islands. Their expedition was studying the tectonic evolution of the eastern Coral Sea. They were geologists interested in the structure of the region. For 25 days, the research vessel moved between sites, collecting information about the seafloor. This was serious marine science. And Sandy Island was essentially a side mystery. During one transit, the team noticed the discrepancy. Their scientific dataset showed the island. The navigation chart used by the ship's master did not. That alone was curious. Navigation charts are designed around physical safety. If a 25-kilometer island exists, sailors need to know. Yet the chart trusted to keep the ship from hitting things said there was nothing there. So the scientists began asking, which map was correct? The research ship passed close to the supposed island and directly over the nearby bathymetric high represented on the legal hydrographic charts. Their sonar measured the bottom, about 1,300 meters down at the shallowest point along their track. Open ocean above. No beach. No trees. No sand. No reef. No island. The result was funny enough that the scientists called it an undiscovery. Most scientific expeditions hope to discover something. They had discovered that something wasn't there. But this wasn't a trivial correction. The supposed island was about 25 kilometers long and 5 kilometers wide in some databases. Imagine deleting Manhattan from a map. Now imagine discovering Manhattan had never existed. That is roughly the cognitive scale of the surprise. How could modern global mapping systems retain an object that large? The media loved it. Headlines spread around the world. Scientists had undiscovered an island. Google Maps contained phantom land. People naturally focused on Google. Google Maps had become synonymous with digital geography for ordinary users. If Google shows a restaurant, people drive there. If Google shows a road, people follow it. If Google shows an island, most people assume somebody has checked. But blaming Google missed the deeper story. Google had not dispatched a 19th-century whaling ship. Google had not invented the original sighting. The company had integrated geographic data from external sources. Sandy Island was older than Google by more than a century. This wasn't primarily a story about one technology company making a bad map. It was a story about data lineage. Where does information come from? When you see a line on a digital map, who measured it? Was it measured directly? Was it copied? Was it inferred? Was it digitized from another chart? How old was that chart? What uncertainty did the original observer have? And did that uncertainty survive the copying process? Sandy Island's history shows what can happen when uncertainty disappears but the data survives. The original 19th century report may have been tentative. Later charts marked existence doubtful. But somewhere in digital conversion, an island is difficult to represent as maybe. Computers prefer categories. Land. Water. 1. 0. Polygon present. Polygon absent. The nuance can disappear. A doubtful island becomes coordinates. Coordinates become a coastline. A coastline becomes a landmask. And by the time the information reaches the end user, there is no label saying. A whaling ship reported something around here in 1876, but several later surveys couldn't find it, so don't take this too seriously. There is simply an island. This is a much larger problem than maps. Modern life depends on layers of inherited data. Credit systems. Medical records. Weather models. Financial databases. Search engines. Artificial intelligence. Scientific models. Each uses information created somewhere else. The output may look new. The underlying assumption may be old. And the older an assumption becomes, the harder it can be to identify. Sandy Island was visible because the error was ridiculous. There should not be 25 kilometers of imaginary land in the Pacific. But what about smaller errors? A coastline shifted 100 meters. A depth sounding copied incorrectly. An old road that no longer exists. A species location misrecorded. A mislabeled geological sample. Most would never produce global headlines. They could still influence research. That is why the scientists who studied Sandy Island after its disappearance treated the case with more seriousness than the humorous headline suggested. They began tracing the genealogy of the island. They examined old charts, modern databases, satellite products, bathymetric grids, hydrographic measurements, and a remarkably clear picture emerged. The phantom could survive because different layers of modern geographic data were less independent than they appeared. The world vector shoreline became especially important. An error there could enter a derived shoreline database. That database could be bundled with mapping software. Other products could use it to mask out land. Google Earth could use coastline information to decide where to display satellite imagery and where to display ocean bathymetry. Sandy Island therefore became visible not because satellites saw an island, but partly because software had been told one was there. On Google Earth, the feature famously appeared as a black elongated polygon. That black shape looked mysterious. Some people wondered whether imagery had been intentionally hidden. That interpretation is understandable. A black patch on a satellite map invites suspicion. Secret base? Classified installation? Missing imagery? But the explanation was more mundane and, in a way, stranger. There was no satellite photograph of land because there was no land to photograph. The system expected an island. It had coastline geometry describing one. But the imagery did not contain it. So the mismatch became visible as an absence. The black polygon wasn't evidence of a hidden island. It was evidence of two databases disagreeing with reality in different ways. And actual satellite images were available. When researchers examined Landsat and other imagery over the location, they saw what the ship had seen. Water. No island. No obvious shallow reef. No vegetation. Nothing resembling the enormous feature drawn in the global coastline. Even biological clues argued against it. Shallow tropical reefs often affect surrounding ocean color and biological productivity. Nearby real reefs produce recognizable signatures. Sandy Island's supposed location did not behave like them. Then there was gravity. Satellites can infer aspects of seafloor topography by measuring tiny variations in sea surface height caused by gravitational differences below. Large underwater mountains exert slightly different gravitational attraction than deep flat seafloor. The technique is powerful but indirect. The region around Sandy Island does contain geological structure. There is a gravity anomaly west of the Phantom Island. That may have contributed to some bathymetric models making the region appear shallower than direct ship measurements showed. But it still did not produce a geological object capable of supporting Sandy Island. The ship's sonar remained decisive. Direct measurement. Water. Then more water. Then seabed 1,300 meters down. Sometimes the simplest observation beats the most sophisticated model. This creates a beautiful irony. Humanity had satellites orbiting Earth. Global digital elevation models. Scientific databases. Computer-generated bathymetry. Internet maps available instantly anywhere. And the decisive experiment was still. Sail there and look. Modern science is powerful partly because it can model places humans have never visited. But models require ground truth. Or in the ocean, perhaps sea truth. Someone eventually needs to compare the representation with the thing represented. Sandy Island survived because too many systems were representing one another. The research vessel interrupted the loop by asking reality. But we still have not solved the oldest part of the mystery. What did Velocity see? If the whaling ship really reported land near this location in 1876, and modern measurements show there was no island, something has to explain the observation. One tempting idea is that Sandy Island was real in 1876 and later disappeared. Islands can disappear. Erosion can destroy low sand islands. Volcanic islands can collapse. Storms can reshape reefs. Sea level changes. So perhaps Velocity saw an island that simply vanished before modern surveyors arrived. The problem is depth. More than 1,400 meters of water. That is not the remains of a small sand island eroded by waves over a century. For land to stand above sea level at that location, there would need to be enormous geological relief. You cannot erode a mountain more than a kilometer downward and leave deep ocean in 136 years through ordinary wave action. Could a volcano have collapsed? Again, the regional evidence does not support an active volcanic island at that precise location disappearing in historical time. There is no appropriate shallow volcanic structure beneath it. So the scientists looked for other explanations. The simplest is navigation error. 19th century navigation at sea was extraordinarily sophisticated by the standards of the time. By 1876, marine chronometers allowed experienced crews to calculate longitude much more accurately than earlier sailors could. But accurate does not mean perfect. Positions could still be recorded incorrectly. Numbers could be transcribed incorrectly. Latitude and longitude could be copied from logs incorrectly. A real island could be observed but assigned the wrong coordinates. That could explain a phantom. Perhaps Velocity saw some other feature and Sandy Island was born from a positional error. But another explanation is more visually interesting. Maybe the sailors really did see something exactly where they said they did. Something large. Something that looked enough like land to put on a chart. But something that was not land. Pumice. Pumice is volcanic rock filled with gas bubbles. Some pieces are so light they float. When underwater volcanoes erupt explosively, they can release enormous quantities of pumice onto the sea surface. Individual pieces gather together. Wind and currents concentrate them. And the result can become what scientists call a pumice raft. The word raft makes it sound small. It doesn't have to be. Pumice rafts can stretch for kilometers. From a ship at sea, particularly in 19th-century conditions, a huge raft of light-colored floating volcanic rock could appear surprisingly solid. Imagine approaching an unfamiliar horizon. No satellite navigation. No aerial imagery. No internet. The water ahead appears covered by a mass of pale material. Perhaps waves break differently around it. Perhaps debris accumulates. Perhaps the raft is thick enough to support objects on its surface. From a distance, what category would you choose? Foam? Reef? Shoal? Island? The pumice theory gained credibility because scientists already knew the coral sea lies along a remarkable transport route for floating volcanic material. Volcanic arcs to the east and northeast produce pumice. Ocean currents and wind can carry that material westward toward Australia. Researchers studying a major eruption near Tonga in 2001 and 2002 tracked pumice traveling more than 3,000 kilometers. Its path passed extremely close to the supposed location of Sandy Island, within roughly 20 kilometers. That is an extraordinary coincidence. Not proof that the same thing happened in 1876, but proof that giant floating pumice rafts can naturally travel through exactly this region. And then, almost perfectly timed with the Sandy Island rediscovery, nature provided another demonstration. In July 2012, only months before the Southern Surveyor expedition, an underwater volcano called Hava erupted north of New Zealand. The eruption produced an enormous pumice raft. Aircraft and ships observed it. Satellites photographed it. The floating field was astonishingly large. Hundreds of kilometers across in its broadest extent. Far larger than the Sandy Island shape. If sailors in 1876 encountered something like that without modern geological knowledge, could they have interpreted part of it as land? Absolutely possible. There is even something poetically satisfying about the idea. Sandy Island may have existed. Not as an island. As a temporary imitation of one. A floating landscape born from a volcano somewhere else, carried across the Pacific by currents, observed once, recorded permanently, and gone before the next ship arrived. One moment of moving rock transformed into 136 years of stationary geography. But we have to keep one word attached to that explanation. Maybe. There is no surviving sample from what Velocity saw. No photograph. No detailed scientific description proving pumice. No way to rewind the Pacific Ocean to 1876. The original observation may simply have been a positional or transcription error. The pumice raft is an intriguing hypothesis because we know pumice travels through the area and can reach enormous dimensions. It is not a solved answer. And that uncertainty is what makes Sandy Island more than a story about bad data. The modern mystery is solved. The island does not exist. The database history is largely solved. We understand how it propagated. But the first observation remains open. Someone may have seen something. We just don't know what. That gives Sandy Island two lives. Its physical life, if we can call it that, may have lasted hours or days as a pumice raft. Its informational life lasted more than a century. And the informational version was far more durable. This raises an interesting question. When did Sandy Island actually stop existing? If it was never geological land, the obvious answer is never. But from the perspective of human knowledge, it existed quite successfully. Cartographers drew it. Databases stored it. Software processed it. Scientists masked data around it. Google displayed it. People searched for it. Coordinates pointed to it. An object does not need to be physically real to have consequences. A false belief can influence navigation. A false record can influence science. A non-existent island can occupy storage space on servers and appear in mathematical models. For years, Sandy Island had a digital footprint larger than many real islands. This is a surprisingly modern form of existence. We spend increasing amounts of our lives interacting not directly with reality but with representations of reality. A navigation app represents roads. A weather model represents the atmosphere. A bank account represents money. A medical record represents a body. A social profile represents a person. Usually the representation is close enough to reality that we stop noticing the difference. Then something like Sandy Island appears. And suddenly the gap becomes visible. The map is not the territory. That phrase is famous because it sounds philosophical. At Sandy Island, it became literal. The map contained territory. The territory did not. But before we become too smug about 19th-century sailors or digital cartographers, consider the scale of the task. Earth's surface is enormous. More than 70% is covered by ocean. Much of the seafloor has never been mapped directly at high resolution. Satellites can infer broad structures. Ships provide detailed tracks. But ship sonar measures narrow paths compared with the enormous area of the ocean. A modern global map is therefore a mosaic. Direct observation here. Interpolation there. Satellite inference elsewhere. Old hydrographic soundings. New multibeam surveys. Different resolutions. Different dates. Different confidence levels. The clean image on your screen hides that complexity. It has to. A useful map cannot cover the entire Pacific with warning labels explaining every uncertainty. But those uncertainties still exist. Sandy Island was simply unusually obvious. 25 kilometers of non-existent land is difficult to ignore. There are subtler mismatches all over the world. Coastlines change. River channels migrate. Glacier retreat. Sandbars move. Volcanoes create land. Erosion removes it. Human construction extends shorelines. Maps chase a moving planet. Even if every coordinate were correct today, some would eventually become wrong. This is why mapping is not a finished project. There will never be a day when humanity announces, "The Earth has now been completely mapped." No updates required. A map is a snapshot of knowledge. Sandy Island survived because one old snapshot was copied long after better snapshots existed. And here we reach the part of the story that may matter most. The island had already been removed from authoritative navigation charts decades before the 2012 expedition. France had removed it in 1974. Australia followed. Professional hydrographers knew it wasn't there. Yet global scientific datasets still contained it. This means the problem was not lack of correct information. The correct information existed. The problem was propagation. The correction did not travel through the information ecosystem as effectively as the error had. That happens everywhere. Bad information is often easy to create. Corrections require effort. A wrong fact can be copied instantly. To correct every copy, you have to find every place the fact went. Sandy Island had entered databases that had entered other databases. Removing it from one chart did not automatically remove it from every derived product. The error had descendants. Imagine changing someone's name in one government system. Another database was copied 5 years earlier. A third company imported that database. A fourth service cached the third. You correct the source. The old name keeps appearing. Now scale that problem to global geographic data accumulated across decades. This is how ghosts survive inside information systems. Not because anyone actively believes in them, Because nobody has traced every dependency. Sandy Island was a dependency problem disguised as geography. When the 2012 story exploded across the internet, scientists around the world began checking. Historical maps were pulled out. Mailing lists filled with discussion. Database maintainers investigated their sources. Within days, the genealogy became clearer. Within months, major datasets began removing the feature. Google deleted the black polygon and the Sandy Island label. Global shoreline databases were updated. Bathymetric products were corrected. An island that had survived from Victorian whaling into the age of smartphones disappeared with remarkable speed once the right people focused on it. That contrast is striking. More than 100 years to accumulate the error. Days to expose it. Months to erase much of it. This is the positive side of connected information. The same networks that spread mistakes can spread corrections. The same scientific community that inherited the error could collaborate globally to trace it. People examined different pieces. One researcher knew hydrographic history. Another knew satellite imagery. Another knew shoreline databases. Another knew oceanography. Another knew pumice. The solution did not come from one genius suddenly announcing the truth. It came from many people comparing evidence. That is how good science often works. Not as a straight line from ignorance to discovery. More like debugging. Something doesn't make sense. Check the instruments. Check the map. Check the old map. Check the database. Check who copied the database. Check the satellite. Check the ship measurements. Check the geology. Gradually, the contradiction becomes useful. Sandy Island was valuable precisely because it was wrong. If the island had existed, nobody would have learned anything unusual from it. Its absence exposed how global geographic data was assembled. A phantom became a diagnostic tool. There is another beautiful detail in the story. When the scientists wrote their formal account in 2013, they gave it the style of an obituary. Sandy Island, 1876 to 2012. As though a place had lived for 136 years and finally died. That joke captures something deeper. The island did have a biography. Birth, an observation from velocity. Childhood, adoption by nautical charts. Adolescence, growing doubt. Attempted death, removal from official hydrographic charts. Resurrection, digital databases. Celebrity, Google Earth. Final exposure, Southern Surveyor. Death, deletion. It is one of the only geographical features whose life story is almost entirely documentary. Its major events happened on paper and inside computers. The ocean itself remained largely unchanged. That creates an unusual inversion. Normally maps record changes in the world. Here, the world stayed the same while the map changed around it. Sandy Island appeared. Became doubtful. Disappeared. Returned digitally. Disappeared again. All while the Pacific kept rolling over the same deep seafloor. If you sailed to the coordinates today, there would be no monument. No marker. No sign saying Sandy Island used to be here. Only water. The phantom has no ruins. And yet, for anyone interested in how humans know things, those coordinates are almost a landmark. They mark the location where a modern society discovered that one of its baseline assumptions about the planet had been copied from a 19th-century mistake. There is a tendency to believe technologies like satellite mapping ended the age of geographic mystery. They did transform it. Nobody today expects a hidden continent to suddenly appear between known countries. Commercial satellites repeatedly photograph most of the planet. GPS tells ships where they are with extraordinary precision. Radar sees through darkness. Sonar maps beneath water. But technology doesn't eliminate uncertainty. It changes where uncertainty hides. In 1876, uncertainty was on the horizon. Is that land? Where exactly are we? In 2012, uncertainty was inside the database. Where did this polygon come from? Which product copied which coastline? Was this elevation measured or assumed? The mystery moved from navigation to metadata. And metadata is harder to see. A sailor knows when he cannot see through fog. A computer user may not know when a data source was digitized from a century-old chart. The screen looks equally confident either way. This is why visual Polish can be dangerous. An old chart containing ED beside an island openly communicates uncertainty. A sleek digital map drawing a solid coastline may communicate certainty even when the underlying evidence is weaker. The improvement in appearance can accidentally hide the weakness in knowledge. Sandy Island became more visually convincing as the underlying case for its existence became less convincing. That is almost the perfect metaphor for bad information. The better it is presented, the easier it becomes to trust. So how should we think about maps after Sandy Island? Not with paranoia. The fact that one phantom island survived does not mean Google Maps is full of imaginary continents. Modern cartography is extraordinarily accurate compared with anything available to earlier generations. Hydrographic surveying has improved dramatically. Satellite imagery makes large land features extremely difficult to invent accidentally. Corrections can propagate quickly. The lesson is not that maps are unreliable. The lesson is that reliability comes from process, not appearance. A trustworthy map is trustworthy because observations are checked. Sources are documented. Corrections are incorporated. Uncertainty is understood. Not because the coastline is drawn beautifully on a high-resolution screen. And sometimes direct observation remains essential. The scientists aboard Southern Surveyor had every technological reason to stay on their original research mission. They already had a legal navigation chart telling them no island existed. They could have assumed the issue was a database artifact and moved on. Instead, they measured. That small decision gave the world a remarkably clean demonstration. The map says land. The sonar says 1,300 meters of water. There is no argument left. Once the ocean is a kilometer deep, the island cannot be hiding. That moment is almost comically satisfying. Imagine the bridge. GPS position approaching the coordinates. Scientists looking at screens. Someone looking through binoculars. Nothing. Then the depth numbers remain large. 1,200 meters. 1,300. No upward slope toward a coast. No reef. No breaking waves. The ship continues. The supposed island remains behind them. Except nothing has passed. They have sailed beside a place that existed only in information. And perhaps somebody aboard laughed. Because sometimes science produces an answer so clear it becomes funny. But the deeper question remained. How many sandy islands are there? Not necessarily literal islands. Errors embedded in systems because every new user assumes somebody before them already checked. The question applies to scientific literature. A claim appears in one paper. Another cites it. A textbook repeats it. A generation later, somebody examines the original experiment and discovers the conclusion was more tentative than everyone remembers. It applies to business databases. A company record is wrong. Other companies buy the data. The error spreads. It applies to history. A dramatic anecdote appears in one memoir. Biographers repeat it. Eventually the story becomes common knowledge despite resting on one unreliable source. And now it applies to artificial intelligence. Systems learn from enormous collections of human information. If the same false claim has been copied across hundreds of websites, repetition can make it appear well supported. Sandy Island is an unusually literal warning about that. Copies are not evidence. Agreement among dependent sources is not independent verification. The only way to know how much confidence a claim deserves is to understand where the information came from. Source lineage. That sounds technical. It is really just asking, who actually saw this? In Sandy Island's case, the answer eventually became uncomfortable. A whaling ship reported something in 1876. Later professional surveys did not find it. French authorities removed it. Australian authorities measured deep water. But the old geometry entered a digital shoreline database anyway. And then the database became more influential than the observers. The representation outranked reality. Until reality was measured again. There is one final possibility worth exploring. What if the velocity report was perfectly honest and surprisingly accurate? What if the sailors really did encounter an enormous pumice raft? Then the story becomes even stranger. Imagine a volcanic eruption somewhere to the east. Perhaps hundreds or thousands of kilometers away. Underwater pressure falls as magma rises. Gas expands. An explosive eruption fragments magma into pumice. Millions upon millions of porous pieces reach the sea surface. They float. At first, the raft may be dense enough that very little open water is visible between pieces. Waves move through it strangely. Rafts can gather logs. Marine organisms attach themselves. Wind pushes the surface. Currents steer the mass westward. Weeks pass. Months. The raft travels farther than most ships of the era ever would on a single route. Eventually it enters the Coral Sea. A whaling ship approaches. The crew sees an enormous pale surface. Maybe it is foggy. Maybe visibility is poor. Maybe they do not attempt to land. Maybe breaking waves or accumulated material gives the impression of a low sandy island. They record a position. They move on. The pumice keeps moving. Days later, the coordinates contain open water again. But the observation has entered a log. The log enters hydrographic information. The information enters a chart. The chart outlives the pumice by more than a century. If that happened, Sandy Island was created by a perfect collaboration between geology and bureaucracy. A volcano made the illusion. Humans made it permanent. It is a wonderful theory. And we may never know whether it is true. The original 1876 event is too distant. No one aboard Velocity can explain what they saw. No photograph survives to settle it. No sample labeled Sandy Island pumice. The Pacific erased the physical evidence. That is why the pumice theory should remain an intriguing possibility rather than the final answer. And perhaps that is better. The mystery ends with something still open. We know there is no island. We know modern datasets inherited an old error. We know how the error propagated. We know enormous pumice rafts can travel through this region. But we do not know what one group of sailors saw almost a century and a half ago. Sandy Island is solved everywhere except at its beginning. That gives us a strange chronology. At the end, certainty. At the beginning, mystery. Usually history works the opposite way. We know how things start and lose details as time passes. Here, the modern investigation removed layers backward until it reached one 19th century observation that cannot be opened any further. Velocity. 1876. Something on the horizon. A position written down. Then silence. Whatever the sailors saw disappeared. But their information didn't. And that may be the real story of Sandy Island. Information can survive its object. A photograph can outlive a person. A law can outlive the government that wrote it. A rumor can outlive everybody who knows whether it was true. And a map can outlive the landscape it claims to represent. In this case, the map outlived a landscape that may never have existed at all. By the time the 21st century arrived, humanity could photograph the Earth from orbit. Ships could know their positions within meters. Sonar could measure the seafloor beneath thousands of meters of water. Yet an error from the era of whaling vessels remained embedded in some of our most sophisticated representations of the planet. Not because modern technology had failed to gather better information. The better information existed. Because old information had been copied more efficiently than it had been questioned. That is what finally changed aboard Southern Surveyor. Somebody questioned it. The scientists looked at one map, then another. They noticed disagreement. They did not assume the more modern-looking dataset must be correct. They checked, and the Pacific gave a very clear answer. Nothing. That nothing became a discovery. Within weeks, scientists around the world were tracing databases and charts. Within months, Sandy Island began disappearing from digital products. The false polygon vanished from Google Earth. Global coastline databases were corrected. Bathymetric models were updated. The world's map became slightly more accurate. Not by adding a new place, by removing one. There is something refreshing about that. Exploration is usually imagined as filling blank spaces. A ship reaches an unknown coast. A mountain receives a name. A satellite reveals a hidden structure. But knowledge also advances by subtraction. Discovering that something isn't true. Removing a false certainty. Deleting an island. The blank space left behind can represent progress. Today, if you look west of New Caledonia toward the old coordinates of Sandy Island, you find what hydrographers had already known for decades. Ocean. Deep ocean. The nearest real reefs and islands remain where geology put them. The phantom is gone. But zooming into those coordinates does not quite end the story. Because somewhere beneath the clean modern map lies a chain stretching backward. Digital shoreline. Paper chart. Hydrographic report. Whaling ship. A sailor looking across the Pacific in 1876. Perhaps seeing land. Perhaps seeing pumice. Perhaps simply writing down the wrong position. One observation. One mistake. One uncertain moment. Copied forward for 136 years. That is how Sandy Island survived. It didn't need sand. It didn't need rock. It didn't need trees. It didn't even need to break the surface of the ocean. All it needed was to be written down. And believed long enough for the next map to copy it. Then the next. Then the next. Until eventually an island that did not exist became part of the digital Earth. And more than a century later, a group of scientists sailed close to where the world told them land should be. They looked out from the deck. They watched the sonar. The ocean floor remained more than a kilometer below. And Sandy Island finally disappeared. Not beneath the waves. From the map.